Okay, now we're going to go into individual equations where if you take the the combined gas law and only if you just talk about the pressure and the volume part of it rather than the temperature, if you just ignored the temperature, all right? And this law is Boyle's law. Okay, so you have to kind of remember the name of the scientist with the law. And his law is P1 V1 equals P2 V2. Notice we do not have a temperature component in this one. It's just pressure and volume. All right, and these are inversely proportional. It means it's the opposite. If you look on the next slide, oh, they actually don't show it, but it's inversely proportional where P is proportional to 1 over V. Okay, this little alpha symbol right there means how are they related to each other. Okay, and they are related to each other by being an inverse. As pressure goes up, volume goes down. Okay, as the pressure goes down, then the volume goes up. Okay, and you can kind of see this. All right, high pressure, you see how the pressure is going up? I got a very small volume. All right, very large volume, very small pressure. All right, another perfect way is a cylinder. Like at the beginning of these slides, they actually show a cylinder. So let's say I have a cylinder here, and I press the plunger down. Okay, this has large volume but very small pressure. When I push that plunger down, I have very large pressure but a very small volume. Okay, so they are related by an inverse relationship. All right, now in lab, either we've done the lab already or we will be doing the lab where we actually do a Boyle's law equation, and you're actually going to get points where you have volume versus pressure, and it's going to be kind of this kind of graph to it. But then you're going to change on the software your pressure. You can't see this. Let me bring this down. You are oh, I can't even bring it down. There we go. You can kind of see that it regraphed it with 1 over pressure. All right, this is volume versus pressure. This is volume versus 1 over pressure. It's the inverse. Okay, and notice you get a perfectly straight line. That's because that's the relationship to each other, the mathematical relationship. So when we do this lab in class, just remember you're going to have to do that. Or if you've already done it, then you know exactly what I'm talking about. Okay, here's a simple problem. You can do this on your own, but basically you have a V1, okay, and you have a P1 and you have a P2, and you're looking for V2. You're solving for V2. Okay, so pretty straightforward. Next one is Charles' law. All right, Charles is a relationship between volume and temperature, and this equation is V1 over T1 equals V2 over T2. Okay, and again, we're getting this from the combined gas law. Remember I showed you the combined gas law, the very first problem we did? Well, we're assuming that pressure is constant, so that comes out of the equation. Okay, it even tells you constant pressure. So we don't include those in the equation, so this is your equation now. V1 over T1 equals V2 over T2. So all you're dealing with are those, so it makes the equation even easier. Okay, and these are directly proportional. All right, volume and or temperature. As your temperature goes up, your volume goes up. Think about a soda bottle. Imagine you take your soda bottle, it's closed, and you keep it in your hot car over summer for a few hours, and you come back, the gas in that bottle is like it wants to explode out, right? As soon as you open the container, it's going to explode out. All right, so high temperature, high volume. This is actually a great example. I don't know if you've ever seen liquid nitrogen. This is the liquid nitrogen. So I have air in a balloon, and liquid nitrogen is very, very cold, very cold. All right, when you pour it on the balloon, it shrinks the balloon because it liquefies all the gas inside of here. All right, it cools it down so much that all the gas molecules start lose a lot of its energy, and you can actually shrink the balloon down. All right, so this is Charles' law. Okay, again, here's just kind of another problem. Here's a sample problem. We're going to do one of these Charles. I'm sorry. Yeah. Sorry. Never mind. Next one is Avogadro's law. Avogadro is volume in moles. All right, this is V1 over N1 equals V2 over N2. Now, I'm not going to supply these equations for you on the exam, just so you know, okay? I will have the combined gas law, and you have to figure it out based off of the combined gas law. You have to know what Avogadro's law is, what Boyle's law is, what Charles' law is, all right, and Gay-Lussac's law, which is not on these slides, but we'll talk about it soon, and we'll learn about it in lab. All right, so this is volume in moles, okay? Um, and finally, the last one, it's not here, is Gay-Lussac's law. Gay-Lussac's. All right, and we're going to be doing this, I think there's two C's. It's either two C's or two A's, I can't remember. Let's make it. All right, Gay-Lussac's is pressure versus temperature. All right, and these are directly proportional, pressure and temperature. Okay, I'm sorry, was it pressure? Because we did volume and temperature, correct? Yeah, we did volume. Yeah, it's pressure and temperature. Pressure and temperature. As temperature goes up, the pressure goes up. All right, and this is P1 over T1 equals P2 over T2. Okay, pressure and temperature, same thing. Imagine you have, I don't know, a balloon, or not a balloon, but again, a soda bottle, okay, and you increase the temperature, what happens with the pressure? It drastically increases. Again, it wants to explode out. The pressure increases, the volume increases. Those are both Charles' law and Gay-Lussac's law. So Gay-Lussac's is pressure and temperature. Charles is volume and temperature. Boyle's is pressure is 1 over volume. And Avogadro's, which we just learned, is volume with respect to moles. Okay, so those are all the equations with the appropriate scientists. All right, and when we come back, we will talk about Dalton's law of partial pressures.